All right, so we're going to start talking about scientific notation because it's a very convenient way to write certain types of numbers. So first, let's go back and talk about standard notation. So standard notation is when a number is completely written out using numerical digits. So it's normal, the way we're used to looking at it. 2, 3, 1,000, 1,000,000. Those are standard notation numbers. They're just the number. But once we start to get very large numbers or very small numbers, it's a little inconvenient to look at it that way. So we have scientific notation as a way of writing very large or very small numbers. A number is written in scientific notation when a number between 1 and 10 is multiplied by a power of 10. So between means the number needs to be greater than 0 and less than 10, but not, that should say 0 or 10. 1 is allowed, so even though it says between 1 and 10, 1 is allowed, but 10 is not allowed. It needs to be a single digit in the front, and we're going to practice this so you know what I mean, but it needs to be a single digit in front of the decimal. It can't be 2 digits, it can't be a 0. So it has to be numbers 1, 2, 3, 4, 5, 6, 7, 8, or 9. That's how we write scientific notation. So I do need to change that. That should say 0, not 1. So let's go ahead. There's this little video I'm going to have us watch really quick because it's cute. It's from a movie.
Something measurable in the biology of the forest.
Which is what exactly?
What we think we know is that there's some kind of electrochemical communication between the roots of the trees, like the synapses between neurons. And each tree has 10 to the 4th connections to the trees around it. And there are 10 to the 12th trees on Pandora.
Which is a lot, I'm guessing.
It's more connections than the human brain. Get it? It's a network. It's a global network, and the Navi can access it. They can upload and download data, memories, at sites like the one you just destroyed.
All right, so if you don't know what that's from Avatar. I just liked that when they throw math into movies a little bit so we can kind of see that. So I wanted to take a look at those numbers that she just threw out there. Because there we go. Sorry. So Pandora tree connections. We're going to take a look at that. So she said 10 to the 4th connections from tree to tree. So that's 10,000 connections from one tree to the next. And then she said there's 10 to the 12th trees on Pandora. So look at all those zeros. Oh my goodness, that's a lot of trees on Pandora. And remember, each tree from one tree to the next has 10,000 connections. So we would actually have to multiply those two numbers to get this very large number here. And I'm not even going to attempt to remember what that number is, just because it's pretty far out there. We've got a whole lot of zeros there. So this is quite a lot. And then she said that's more than the human brain. So that's 10 to the 15 connections. And I just grabbed that off the internet. There's a couple of different I guess, opinions on how many connections the human brain has. So this was just one that I had grabbed off of a search. So don't fault me if I'm wrong on that one. I'm just kind of guessing there. So that would be, here's the zeros we have here. So, oops, we can see, yep, this one is definitely bigger than this number. There's more connections from tree to tree on Pandora than there is in the human brain. So it's kind of like this massive planet brain with all these connections. So a tree from one side of the planet can talk to a tree on the other side of the planet. Theoretically, if they're all connected like that, they can talk to each other. So it's a very interesting idea that they have on that planet. But it was just a lot of big numbers she threw out there. So whoa, that's a lot of numbers. So it's much easier to deal with that in scientific notation. So that's why she says 10 to the 4th and 10 to the 12th. That's an idea of scientific notation there. It's a way of writing it much smaller than saying those huge numbers that she was trying to say. Even though the other actor there said, I assume that's a big number, because he was trying to argue with her. So we're going to learn about scientific notation because it's a much easier way to deal with these types of numbers, okay, than the actual, standard notation number. Okay, so here we have two examples of scientific notation. You can see we have a very large number and we have a very small number. So this is two examples of why we would use scientific notation. So we can see there's a coefficient on each one. So this is the number, and it's always going to have a number between 1 and, it says between 1 and 10, but it's between 1 and 9, because it can't be 0 on the front and it can't be 10. It can't be a 2-digit number. It has to be a 1-digit number. So we move the decimal place over until we get to that one essential number. That's called our coefficient. We always have it times a base of 10, and the exponent actually tells us is it a big number or a small number. So if it's a positive exponent, it's a large number. If it's a negative exponent, it's a small number. So it tells us it's a decimal or it's not a decimal. Really, that's what the exponent lets us know. So we're going to go ahead and practice how we put these in and out of scientific notation on the next slide here. First, we're going to deal with scientific notation with positive exponents. So with a positive exponent, this means we're dealing with a large number. So if it's positive or negative, that means different things. Positive exponents means it's a large number, meaning that it's larger than 0. It's larger than 1. Doesn't have to be much larger, but it needs to be a whole number, not a decimal. Okay, so that's what positive means. So we want to make sure we're paying attention to the direction here. So when we're putting it into standard notation, that means we're starting with scientific notation. This is what we want to do. So the number 2 times 10, and that's to the 5th, I don't know why that got cut off a little bit, is written in scientific notation. It has a number between 1 and 10 multiplied by a power of 10. So we can see that it has a number between 1 and 10. 2 is between 1 and 10. And it's multiplied by a power of 10. So it's always going to be times 10 to some exponent. That's how we write scientific notation. To write in standard notation, we do the multiplication. Or really we're going to move the decimal place out. To multiply 2 by the power of 10 to the 5th power, we simply move the decimal 0.5 places to the right. So that's the exponent just tells us which way we're moving and how many places to move. So since it's a positive exponent, I'm going to move to the right because I want to make that a big number. If I moved it to the left, I'm going to have a very small little decimal. Okay, so just make sure you're paying attention. Is it supposed to be a big number or a small number so you can logically move it in the right direction here. So you move it 5 times, and now the decimal is in this place. So we would also need to make sure we put our commas in here. So this is 200,000. So this is a way of writing 200,000 in a kind of a smaller format. So we can see we're moving to the right. So I'm talking about moving the decimal. So now if we're putting it into scientific notation, I don't know why it's cutting off some of the letters here. So now we're starting with a very large number. So we have 11,700,000, and we're going to put this into scientific notation. So we know it's a very large number. Right away, I'm going to have a positive exponent. Make those connections because that's much easier to keep track of as you're going. So we need to write it as a number from 1 to 10 multiplied by a power of 10. So our first job is to move the decimal point to the very first number in the number we're given. So we're going to move this decimal point. We're just going to keep bouncing it to the left until we get to that first number. We don't want to go past it. We want at least one number in front of here. Well, we need only one number in front of there. But remember, it can't be 0. It has to be 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we get 1.17 with a bunch of zeros on it. And these are non-essential zeros. There's no other numbers other than 0, so we drop them off. So we only have 1.17. Much easier to look at than the 1.17 with all those zeros on the end. So if they're non-essential numbers, meaning they're just all zeros, we drop them off. Although if there was a single, even if there was a 1 on the end here, now they're essential, and I can't drop them off. So if there was a 1 on the end here, that's probably not a very nice number to write in standard or in scientific notation. So we move the decimal point 7 places. That's how many times we jumped here to the left. So we multiply 1.17, that's the decimal we ended up with, by 10 to the 7th power. So it's always power of 10, and then the exponent is how many times did I move it to the left. So if you notice, putting it into standard notation, if I'm already in scientific, I'm moving it to the right to make that a large number. If I'm starting with standard notation and it's a large number, I'm moving the decimal to the left until I get to that very first essential number, so that that's the beginning of my decimal. So 11,700,000 is 1.17 times 10 to the 7th power. And we can actually read this a lot of the time when we hear scientific notation in the real world. We would hear 1.17 million. That's actually a more common way of saying it. Instead of saying times 10 to the 7th power, when you hear like 1.2 million, that's actually scientific notation. It's just a different type of science. They're just using a different way of saying it. And that's not always the best scientific notation, because you can also hear like 34.2 million. Okay, well, the 34 shouldn't actually be 34. It should be 3.42. And then they would change that a little bit. So you wouldn't actually say 3.42 million, because that would change the number. So throwing some extra numbers out there. Hopefully that's not confusing. So we move to the right to put it into standard notation. We move it to the left to put it into scientific notation. So make sure you understand which direction am I moving. All right, let's practice that a little bit. Oh, I had highlighting on here and I totally forgot about it. That would have been a little nicer to follow along on. All right, so now we're going to practice a little bit. All right, so we're going to write 8 times 10 to the 3rd power in standard notation. So we're taking this out of scientific, and it's a positive exponent. So we're going to move that decimal to the right. So we have 8. Here's my decimal point, because it's not there. If you don't see a decimal point, it means it's literally right after. And I'm going to take that and I'm going to move it 3 times. So I'm going to go 1, 2, 3. And each one of those jumps gets filled in with a 0. If there's no number there, it's a 0. So this number is 8,000. All right, we're all done with that one. Now let's do the next one. By chance, we're using a 3 again here. So it's 6 times 10 to the 3rd power. So there's my 6 with my decimal point, and I'm going to move it 3 times, again, because that's my exponent. So 1, 2, 3. Fill those spots in with a 0. Uh-oh, that should say 6,000, not 8,000. Silly me. Typos here. So we get 6,000. So it's not always going to be a 3. By chance, we just had 2 of the problems here with an exponent of 3, but you're just using that exponent to tell you how many times do I jump to the right to take this out of scientific notation. All right, now we're going to put it into scientific notation for the next one. The total surface area of Europe is approximately 3,930,000 square miles. Write this number in scientific notation. So first, what we want to do, oh, that animated really fast. So we want to take that decimal point that's at the end, and I want to jump over until I'm at that first essential number here, which is the 3. So I don't want to go past the 3, I want to stop right before it. So we move the decimal 6 times to the left, so the exponent will be 6, because that's how many times it moved, right? And so my decimal is going to be 3.93 with a bunch of zeros. Remember, those are non-essential numbers. I can drop those zeros off. I need to make sure I leave the 393. I don't get to drop those off. So darn, computer here. 3.93 times 10 to the 6th power, because I moved it 6 times. All right, so that is scientific notation with positive exponents. I hope that helped, and I will see you in the next video.